Hi, welcome to Study with Rishi, and this is 10-minute system design course where we learn any system design concepts in 10 minutes or less. In this video, we will talk about consistent hashing. But before we talk about consistent hashing, we are required to learn the need of it. And that brings us to the distinction between stateless and stateful systems. We can divide all the systems we see and use around us in two broad categories: stateless systems and stateful systems. Stateless systems means no data about request is stored on application server. So all application servers are equally capable of serving any incoming request. Benefits of it is caching becomes easy, very easy. Caching the information becomes very easy. We can use a centralized cache. Load balancing becomes easy as now all the servers are equal. Adding or removing servers is easy. So basically overall structure becomes easier to handle. On the contrary, in stateful systems, we store context of conversation in application servers. Some systems are inherently stateful. Let us understand this with an example. Let's say there are two servers, server 1, S1, and S2, server 2, on which basically a talking bot is deployed. Now Rishi comes and starts talking to the system. LB or the load balancer diverts the traffic to S1. So S1 stores the context of Rishi, the conversation which we had. Here context is older conversation and variable of history. Now each time Rishi is sending a new request, it must go to S1 only because S1 knows the history of conversation and can reply with correct answers. Load balancers with the help of sticky sessions need to decide which server the request is needed to be sent. One question might arise that why not just bring the context to a central system or a central cache and make the overall system stateless? While it is possible, but in that case, if we just keep one central node, one central cache node, that will become a single point of failure. And if we scale that with a master-slave architecture or a leader-follower architecture, that will introduce latency in the system. So that is the downside of doing that. We will talk about master-slave architecture and leader-follower architecture about the replication system in a separate video. So far we have seen that there can be distributed stateless systems but distributed stateful systems also. Now let's talk more on the load balancing and scaling of distributed stateful systems. To use load balancer in a stateful system, load balancer should be able to use some identifier from request and decide to which app server the request should go. One way of doing that is keeping a map of request ID to server ID, but this will grow very big in very small amount of time, so it will result in a lot of latency. Another way is using a hashing function to decide which app server a request should go to. Say we have 4 app server and we have a hash function which takes in consideration the ID part of incoming request, does ID mode 4 and find the server the request should go to. Issue with such a system is that it will be problematic to handle when one of the boxes die. Once that happens, we will be required to move the session from that server to the live servers, and there is not a way to uniformly distribute load on all the servers. One of the servers will be accepting new traffic, which might result in cascading failure of the complete infrastructure. And this is where consistent hashing comes into picture to evade the cascading failure. So first let's take an example of normal hashing solution, make it fail and then improve it with consistent hashing. Let's say we have 5 app servers and 2 hashing functions. User hash function, which is basically for users and it ranges from 0 to 10 to the power 18, and also a server hash function, which is for servers, and it also ranges same as of user hash function. Now if we represent it on a circle, it will look something like this. Now first step is to calculate hash of servers via their server IDs using server hash function. Say for hash of first server we get 720, for hash of second server we get 10 to the power 14, for third we get 7777, for fourth we get 10017, and for fifth we get 10 to the power 8. Using these values, we mark the point on the circle which represent the server location. Now the second step is using user ID, we calculate hash of it using the user hash function. Say user ID is 616 and user hash for this ID is 10 to the power 5 as output. Mark 10 to the power 5 as user on the circle. Now as per the algorithm, the first app server falling in the clockwise direction will be served by this user. So for each user, the server falling first in clockwise direction will be serving that user. This is the algorithm. Now let's take a situation. we add a new server in the infra. To add a new server, sixth server, we first calculate its hash. Say we get 10 to the power 6 as hash value. Here, all these users which were previously being served by 10 to the power 8 now will be served by 10 to the power 6. Their context will be moved from 10 to the power 8 to 10 to the power 6 server. But all these users which were previously also were served by 10 to the power 8 and now also will be continued serving by 10 to the power 8. This way, disturbance while adding a new server is reduced and no downtime is required. But let's take a problematic situation. Let's remove a server from the picture. If we remove 10 to the power 8 from the picture, all these users will then be moved to 10 to the power 14 server, which will then might become overloaded as total load is now twice on it, and cascading failure will occur, definitely. Something which can occur, it will occur. To solve this problem, we increase the number of server hash functions. Say we have k hash functions now, and each server ID will be hashed by each of the functions. This way, same server will be present at k locations. Now, if one server fails, its user will be given to next server available. But this time, user will be distributed at k different locations. And so, k next available app server will be chosen. This way, we minimize the load increased on each servers by distributing it almost uniformly on all of the servers. The bigger the k, higher the distribution factor, and minimum the load increased on each of the servers. This way, we would save the system from failing due to cascading failure. So this was the video about consistent hashing. If you liked the video, please consider liking it and subscribing to the channel. I am also a mentor at Scalar Academy, and if you have a question around it, I have given my details in the description of the video. Do consider sending me a ping there. In the end, I thank you for watching the whole video. I hope you liked it.